just forgot our efforts, and now we are working routinely at a temperature over 500 degrees. Now we reach about 800 in the cold reactor, outside about 300. So I think this point has to be positive. Thank you.
What I said was that the chastisement was to me. I didn't run experiments at 300 degrees. I ran my experiments at low temperatures. I am well aware of other people working at high temperatures, including your work.
As a short question, Ruby.
When we talk to people and tell them about cold fusion and try to communicate, and for instance, university professors, and they say, well, I got my nature, and nature was pretty clear on this doesn't work. What do I say? How can I respond to that? What is the explanation for this?
Well, a person that makes that statement is not worthy of communication. And that is not at all what the nature conclusion was. The nature conclusion was quite neutral, and it was very clear from what was said by and about the team that they intended to proceed. If they believed that they had demonstrated that the effect was not real, they'd have simply washed their hands and gone on to other things. I think to a man, you can ask Matt about this, to a man and woman, they all intend to proceed because they are excited with what they have seen. Have they solved the problem with $10 million and 4 years of effort? Hell no. We didn't solve the problem with 10 times that amount of money and 30 years worth of work, but that doesn't mean there isn't an effect. So I think what you're listening to is knee-jerk 1989 Luddite thinking. Right? And it's people like that, like wearing their baseball caps backwards. You know, I love that.
Okay. Thank you. Applause to Mr. Nagel. Comparison with medical results of Kalman in Kenzie with Nell's present results.
Good morning. Let me begin by thanking Bill and Claudio for organizing this conference and for having it in such a nice place. It's a real pleasure, and we really appreciate it. So, So I will be talking about theoretical work done by Kalman and Castilli, and have just a little time at the end to compare it with known LENR data. This presentation seeks to invite attention to the work of these two people, and it cannot assert that they have a full and final explanation of the mechanism that causes LENR. There's very good reason I can't assert that. I'm incapable of doing that. There's no mystery there. So we will see that as we go on. So the outline of the talk is we'll have the background on their papers, and then the core of the talk is say the excitation and de-excitation mechanisms. How is it that LENR can occur? And their answer is a combination of Coulomb and strong interactions in a two-part mechanism, and I'll talk about that in detail. And then there's the well-known problem: we don't have energetic particles. We don't have gamma rays. How does that happen? And their answer is the recoil of heavy atoms within the lattice dribbles away the energy, producing heat without high energy radiation. And at the end, I will put up only a single slide on the comparisons, which is sort of a problem. I'd like to talk much more about that, but that's all that time will be made. Okay, so the background is two Hungarian theoreticians, Peter Kalman and Thomas Castilli, published or posted 17 distinct papers over the last several years, 15 years. 9 of the papers appeared in referee journals such as Physical Review C, the European Physics Journal, and John Paul's Journal of Condensed Matter and Nuclear Science. And the rest were posted to the archive server. The works were based on standard quantum, nuclear, and atomic physics, and they dealt with two subjects, the enhancement of deuterium fusion cross-sections at low beam energy, and also the production of LENR. So we really have a two-part talk here, and I'll go into that more in a moment. These two gents are from the Budapest University of Technology and Economics, which is on the Danube River in downtown Budapest. There are a few reasons for paying attention to these papers, okay? They were written by competent physicists. Now, when I say something like that, it may be offensive to some of you who come from different backgrounds. But if you have a car problem, you don't go to a bicycle mechanic. You go to an automobile mechanic. If you have a problem like this, you don't go to a classical scientist. You go to a quantum mechanic. Okay? So these people are very expert and qualified physicists to deal with this problem. They've come forward with qualitatively new ideas. They've written equations based on those ideas and then evaluated them. And they've produced quantitative cross-sections and rates for these reactions. And then they go on to compare their results with data from several types of LENR experiments and also the enhanced DD fusion cross-sections. Now, many of you know what I'm talking about when I talk about enhanced DD fusion cross-sections, but some of you don't. So I have a graph here from the work of Kasagi, and it's a fusion yield from beam experiments conducted at energies of 10, 5, and towards 1 keV for different targets. And what you have here are really two curves, the conventional high energy curve and then the actual data, and this is the ratio of the two. So that as you go down in energy, there is an enhancement by an order of magnitude, almost 2 orders of magnitude in the case of some of the targets, in the fusion cross-sections. So Kasagi, Tversky, many very, very capable experimentalists have been showing up at our meetings for years, giving papers on this, and I've been befuddled because what's the connection between those beam experiments and the experiments, the LENR experiments done at room temperature or even at temperatures like this? There's a large factor between the two. The reason I'm showing this is because the work of Kalman and Castelli bridges this gap. So this is a list of their papers from 2004 to 2019 in the journals involved. I don't want to go into this in detail. What I mean to show is that they address both LENR and the beam experiments. And if you look at this, 11 of the papers dealt with one, 11 with another. That's 22, but 5 of them dealt with both. That's the 17 papers. So they have a vast literature. In fact, here's a printout, two-sided printout of all of their papers. Okay, so when I got into this 6 months ago, thanks to getting one of these papers from Graham Hubler, I tried to trace their ideas. I made up this graphic. The yellow is published work, okay? The gray is posted in the archives server. There was one paper here that was started in 2015 and later updated and so forth. And I used the references in their papers to try and trace the evolution of their ideas. And I sent this to Peter Kalman, and he sent back a graphic, which is going to be in parts. Sorry, I had a different version of this. So he laid out how their ideas evolved over the years from possible solid-state conversion, electron-assisted reactions in the early days. I apologize for this. This is the version of the presentation that I had thought I got rid of. But anyway, this is the authoritative history of their work and their thinking. Okay, and I invite your attention to the lower right-hand corner. Some of the graphics that I show you will have that attribution there, and that means it either came from them or was significantly improved by them. So if I had more time, I would go through and give you the history, okay? But I'm really much more interested in giving you the core ideas, so we'll go on from that. What I look for in a theory is listed here: concepts, equations, calculations, and results. So they have concepts, they're new, okay? And their understanding requires a knowledge of quantum mechanics. The equations can only be verified by somebody with deep understanding of quantum mechanics, and I just pulled out of one of their papers some of the mathematics, okay? This is not easy work. As I say, I cannot fully understand it, okay? But I think it's still worth attention. So then you look at the calculations that they did. It should be possible but difficult to reproduce those. And finally, one can take the results of the concepts, the equations, the calculations, and compare them with the experiments. Okay, so that's the idea. I went through the papers and took out their diagrams listing the types, emphasis types, of nuclear reactions that they treated in their various papers. Okay, you look at this and say, what's going on? This is so complicated. So let's focus on the two more important, namely the upper left-hand corner. Okay, and those are the nuclear caption or fusion reactions, and then nuclear reactions that produce two final fragments. Okay, so what you see in the top is a single outcoming product. I'll explain this in a moment. Or two reaction components. Okay, they treat both. We're going to focus on the first of these, both for simplicity and because fusion is so significant to this community. Okay. So the idea is three particles, atoms or ions, are assumed. Two of them may be in a lattice. It goes back to this is condensed matter nuclear science. They are dealing with that directly. The diagram shows a second order process, okay, in which particles 1 and 2 come together coulombically or electrodynamically to produce the particle 1' and 2'. You see these are indicated here. So the first thing that happens is one of the atoms, a catalyst, interacts with one of the reactants to produce a changed reactant that then goes on to interact with the other reactant. Okay? So particle 1 serves as a catalyst. Catalyzed fusion, not muon catalyzed fusion, very, very different, but still catalyzed fusion. Particle 2, which can be a deuteron moving the lattice quasi-freely, okay, either because it came in from the outside of the beam or was otherwise stimulated to move quasi-freely within the lattice, okay. Particle 3 is another more or less freely moving particle, think of a deuteron that's in a heavily loaded palladium that can interact with a strong interaction. So you have here the Coulomb interaction followed by the strong interaction. Okay. Wrong way, sorry. This is possible because particle 2 in the first interaction was given some high momentum components that enable it to overcome the Coulomb barrier. Okay, that's absolutely essential. That's their answer to why low energy nuclear reactions occur at all. Okay? And I think that's the end of that. So comments on their theory? Okay. Mechanisms. Okay. Particle 2 does not need high energy to overcome the Coulomb barrier. The negligible or near zero energy of the initial state does not change dramatically during the initial interaction. The mechanism is intrinsically quantum mechanical and cannot be understood classically. In a way, it's like superconductivity. You don't have a classical explanation of how two electrons can interact through photons. You can describe it, you can say those words, but it does not give you a quantum mechanical understanding of what's going on in the case of superconductivity. No time difference between the two interactions. They're distinguished as first and second in accordance with the time ordering terminology of quantum mechanics. They're part of a single reaction. Second order terminology is not to be confused with the two-step process. That's, again, a terminology from quantum mechanics. So let's get more real about this. Let's actually show what can happen when you have a palladium atom acting as a catalyst for the fusion of two deuterons. Okay, so you have three particles coming in. If you remember anything about this talk, it's a three-body mechanism. Okay, whether it leads to a fusion reaction, as indicated here, okay, helium-4 produced, or as indicated in the next slide, I'm sorry, palladium helps satisfy the energy momentum conservation. I forgot that. Okay, you can have P and D coming together, produce helium-3, again with the palladium as a catalyst, and the roles of the palladium and deuterium can be reversed. It doesn't matter whether this is the P and that's the D, or vice versa. You can produce helium-3 in either of the cases. Okay, so an overall diagram of what's going on here is shown in this graphic. You have the initial state with three particles, and in the case of fusion, you have a final state that has two particles, the catalyst and the reaction product. The LNR experiments are characterized by having an initial energy and momentum that's very, very small. They can be considered as zero on a scale of the energies and momenta associated with the nuclei. Momentum conservation exists for both interactions, and the nuclear reaction rates depend on the triple product of the densities of all three bodies that come into the reaction, which goes towards explaining why high loading is necessary. So momentum conservation, and this is a very important graphic, the energy released, signified by delta, is taken off by the two outgoing particles, the catalyst particle and the reaction particle, okay? And they recoil in opposite directions, whether it's a helium or something heavier, as well as the palladium, they're moving slowly, okay? And they dribble their energy away by heating the lattice. Okay, so that takes care of the de-excitation part of the problem that we have in this field. If there are two outgoing products, it's basically the same story. They have criteria for transmutations. I don't have time to go into this in detail, but you say nuclear transmutations of elements all across the periodic table have considerable cross-section. So this graphic says that for proton capture and for deuteron capture, no matter what element in the periodic table is involved, there are criteria from their theory to see whether or not those reactions will go. Okay, now, sorry to those of you in the middle and the back, that'll be not readable, but I said earlier there are many types of nuclear reactions that they cover. There are also many specific nuclear reactions. So these are two tables from a recent paper. Okay, fusion is only one of many possible reactions. So if you look at these are catalyzed by nickel. Okay, and nickel with lithium, giving oxygen. Anyway, they give the actual reaction rates for various nuclear reactions. The table on the right is particularly interesting because they assert that transmutations can also occur at the anode that is being mediated by platinum in electrochemical experiments. Okay, so you have many different possibilities here. Now, for the experimentalists, this is a gold mine. You go through here and you look at for a reaction with a fairly high probability, and then you can focus on that and do transmutation measurements. You know, fluid discharge, mass spectroscopy, and other things. So from my perspective, the reason that this body of work is worth paying attention to is because it has so much detail. They use actual lattice constants in their calculations, many details. Okay, so some of you by now are concerned about the dynamics. Particle motion is necessary, okay? If you take a piece of deuterium-loaded palladium, such as Mike and Fran did in their exploding wire experiments, it by itself doesn't react. There has to be some dynamic, okay? There has to be what has been referred to as disequilibrium, okay, in order to get particle motion. But one of the things that surprised me is that the nuclear reaction rates are independent of the magnitude of the relative velocity of the two reactions. How can that be? Well, you go through their mathematics and you find the velocity cancels out. And I wrote Peter Coleman about that, and he came back saying that's also true of the thermal neutron absorption in reactors. That is not velocity dependent. There's a precedent. It's different physics, but there's a precedent. So what are the required sources of motion for various experiments and beam experiments? It's the projectile velocity. In plasma experiments, it's the bombardment of ions from the plasma. Hot gas experiments, atomic bombardment. And in electrochemical experiments, you need a flux of either deuterons or protons, depending on the experiment. How can you get that? Disequilibrium, pulsing things, okay? So they give you a recipe for how to conduct experiments, not only which specific experiments, which combinations of elements, nuclei, but also how to do the experiments. And this statement here is very important. There has been and remains a discussion in the community about LNR being surface reactions or bulk reactions or both. They're talking basically about surface reactions, but they can occur in the bulk in electrochemical experiments if you have high load. Okay? So that addresses that problem. the characteristics and consequences, the mechanisms, equations, calculations, results, and reported features. There's standard quantum mechanics, okay, perturbation calculations beyond first order are necessary. The effective perturbation comes from the initial Coulomb interaction. They explain both enhanced DD fusion cross sections and LNR results at room temperature and hotter. Both the excitation and de-excitation mechanisms are treated and consistent with LNR observations. Explanations of both heat products and transmutations. And the recoil mechanism explains the lack of high energy radiation, and the magnitudes of the recoils are important. The assisting catalytic particle must be heavy because then it moves fairly slowly, even though it might have MEV energy, okay, to produce heat in the lattice. So this is the last graphic that I'll put up. It's a list of the contacts between their theoretical work and LNR data that they have published in their 17 papers. Okay? Nuclear reactions and solids are different. Okay? Mike said this earlier. He attributed the dominant discovery of Fleischmann and Pons being the condensed matter nuclear science. And they explained that. They have information on loading thresholds and how LNR vary with loading thresholds, heat helium ratios, energy production, nickel hydrogen experiments, transmutations, low energy enhanced DD fusion cross sections, heat production without radiation, reasons for diverse results, explanation of isotope changes, and they have a paper on photo-induced reactions. So it would be nice to go through each one of these. I initially had planned to do that. Then I decided that the most important thing that you can take away from this presentation is the fundamental three-body mechanism, where you have the sequential Coulomb interaction followed by the standard nuclear interaction, leading to LNR in general, and then the recoil of the particles, the same three bodies, leading to the lack of high energy radiation. So I had hoped that Kalman and Castillo would come here to give their own presentation. They weren't able to. It was a pleasure working with them in order to prepare this presentation. And I hope you go away from here with an interest in looking at these papers with an eye towards mining them so that Google and others can learn what to do based on this theoretical work. Thank you for your attention.
Thank you very much. It's me, Kasane. Can you hear me? Okay, my question is, can I see the slide which has a diagram? The palladium going to the alpha plus palladium system.
Okay, let's see if I can flip backwards. Tell me when to stop right there.
Yeah, that's okay. Then, that's all right.
Okay.
So in this case, the particle 1 corresponds to palladium, and 2 is the deuterium, and 3 is the deuterium also, and 2' is just a scatter after the first Coulomb scatter. And then it comes to the fusion, makes a helium-4. So you said that energy and momentum conserve with the three-body initial state and just two-body final state. So therefore, conservation, energy and momentum should be due to the helium-4 plus palladium. So in that case, even if the helium is ground state, that means the energy obtained in this mechanism, you get a 20 MeV or more, right? Because DD makes helium makes 20 MeV energy. And these two energy share with the palladium and the helium. That means helium has got larger energy, much larger energy. Like, yeah, that's a mass ratio, you know. So therefore, the helium